Welcome to the lecture series of linear integrated circuits. Today we are going to discuss about the topic instrumentation amplifier. So it is a modified differential amplifier where it is very significantly used in industrial applications for sensible sensor applications. So let us move on to the system. So as we already discussed that the differential amplifier has some demerits like it is having very less CMRR. So the differential amplifier should not amplify the common mode signals. It should amplify only the differential mode signals. So due to the low impedance present and also due to the input offset voltage, the common mode signal problem will arise in the nominal differential amplifier. So due to that, the common mode signal also is getting amplified. Hence the CMRR is very less in case of your normal differential amplifier. So for that, and that is one demerit, and another one is it is having very less input impedance. So for avoiding these two problems, we are just connecting the non-inverting buffer. So these two are non-inverting buffers just connecting to the differential amplifier. So far these resistance stages were not there. These non-inverting buffers are directly connected. So this will also will result in a poor CMRR. So hence to avoid all those things, we are modifying the connections of differential amplifier with some replacing circuits. That is, it is split into two stage. This stage is stage 1. That is, it is input stage. That is input stage. And this one, it is output stage. It is split into two stages where two op amps are used in your input stage and one op amp is used in your output stage. If you see the circuit of this, you are familiar that it is a differential amplifier. See, so the feedback is fed from the output to the inverting terminal, and the two inputs, two signals are connected through R1 and this resistance R1 via the inverting and the non-inverting terminal. So this system is perfectly acting as a differential amplifier. This will differentiate. This will amplify the difference between the voltage present at this node and this node. And in order to improve, as we see the nominal differential amplifier has certain demerits. So in order to improve those demerits, we are connecting the non-old, that is, we are connecting the stage 1 input stage with two buffers along with this resistor combination. So if you see here, this resistance plays a major role, that is denoted as RG, that is gain resistance. So this will provide an improved gain. So these two op amps are normally ideal in nature. So for ideal characteristics, so this RF1, RF2, everything is same, and only this RG is varying resistor. So by varying this resistor, we can improve the gain. And we can give to the multiple stages. So for this reason, we are splitting into two stages, input stage and another one is output stage. So now coming to this stage, so this is one op amp setup, ideal op amp setup, and this is another ideal op amp setup. So if you see here, V1 is connected at the non-inverting terminal and here V2 is connected to the non-inverting terminal. So both the signals are connected to the non-inverting terminal. These two are held as non-inverting buffers. So this circuit is also one of the non-inverting buffers and this circuit is also one of the non-inverting buffers. So if you see the output side, one resistor is connected and it is fed back to the negative. So simply it is a feedback resistance, and here also one feedback resistance is connected to the inverting terminal. So both are working as a non-inverting amplifier. Okay, so this is acting as a non-inverting buffer. And one more thing, so hence we are saying that these two are ideal in nature. So no current will enter into the terminal of an op-amp. Hence, it possesses high input impedance, infinite input impedance. No current will enter into the op-amp. So, whatever the current flowing here, it will directly move to this stage and this stage. So, the same current will flow from here to here, and here to here. And also, the negative feedback is given. So, once the negative feedback is given, automatically the virtual ground concept is come into picture. So, the virtual ground concept, according to virtual ground concept, we can make that V1 and V2 are same. So, sorry, V1 and the terminal present is the negative also V1. So, both are same. So, with this introduction, we will move on to the analysis part. So, we are just naming as this node is A and this node is B. And here it is named as E, G, H and F. So at the node E, the voltage present is V01 and here it is voltage present is V02. So if you see from node A, the potential V1 is connected and node D, potential V2 is connected. So once the negative feedback is given, what I said, automatically the virtual ground concept comes into picture. So according to virtual ground concept, the potential VA equal to VB according to virtual ground concept. So whatever the potential present at node A will present at node B. So now the node A is connected to V1. So the V1 will present in B. Similarly, potential at D is V2. So the potential at C is also V2 according to the virtual ground concept. So now if this terminal is directly connected to the terminal G and here it is directly connected to the H. So the same potential at B will maintain in G. Similarly, same potential V2 is maintained at H. So now V1, V2 are the potential between the node G and H. And between node E and F, V01 and V02. So as I have already said, no current will flow here and in this terminal. So these two op-amp are ideal. So no current will enter. The current flowing from V01 and V02 is same. So with these assumptions, let us apply the Ohm's law between the node E to F. Okay, between these two nodes. So the potential difference between these two divided by sum of the resistance. So the current equation is given as I equal to V01 minus V02 divided by RF1 plus RG plus RF2. This is the first equation. For my assumption, this is ideal. Both are ideal in nature. So I am just representing RF1 and RF2 as equal and naming it as RF. So by replacing this RF1 and RF2 as RF, we are getting 2RF plus RG as the equation 1. Now, this equation is identified. Now coming to the node G and H. So now identify the voltage between these two nodes G and H. So as I have already told, the potential at G is V1 and H is V2. Now take the difference between these two and write the KCL. I equal to Vg minus Vh divided by Rg. So Vg is V1, Vh is V2. So V1 minus V2 divided by Rg. These two are the potential at this points. Now this is also I, this is also I. Hence I am equating these two. So V01 minus V02 divided by 2RF plus Rg, V2 minus V1 divided by Rg. So now if you see the differential amplifier stage, that is output stage, my output is V0 and input is the the voltage present between these two nodes. So here it is taken as V01 and this one is V02. This voltage is directly applied to these terminals. So V01 here the same potential V01 is present and here V02 it is directly connected to R1 and this point also V02. So the inverting and non-inverting terminal input stage will apply V01 minus V0, V01 and V02. Now the differential amplifier input is V02 minus V01. Hence, the non-inverting terminal is connected to V02 and inverting terminal is connected to V01. The difference between the input signal is V02 minus V01 and the output is V0. So, we have to get the relationship between V0 to V2 minus V1. This is my gain, output by input. So, for this, we are doing all this analysis. Now, I am just representing V02 minus V01, just replacing multiply with sign minus. So you will get V1 minus V2 divided by Rg. So now keep this V01 minus V02 minus V01 as in the same. So you take this to right hand side, you will get this equation. So now you know that V01 minus V02 in terms of V0, you will substitute the value whatever the present in here. So you just apply the equation. So we know that the differential amplifier gain value is V02 minus V01 equal to 1 plus RF, minus RF R1 divided by R2 into V1 minus V2. This is your stage. So just substituting here, you will get R2 by R1 into 2RF plus RG divided by RG into V2 minus V1. Now just replace the thing, you will get this equation. So instead of 2RF plus RG divided by RG, you just 1 plus 2RF divided by RG. So if you take V2 minus V1 as left hand side, you will get the gain equation A. So A equal to R2 divided by R1 into 1 plus RF divided by RG. So if you see here, the gain value is directly depend upon the value of resistance RG, since other resistance are common. Also, they are constant. So only variable resistor is RG. So if you want to vary the gain, you can vary the resistance and you can go with different stages of gain values. So this is the overall gain circuit of an instrumentation amplifier. So for this reason, so this is very perfect in case of increasing the CMRR, because so the look into these two node G and H. If common signals are present between these two, V1 and V2, there will not be any difference between V1 and V2. No current will flow through RG. So if only difference in voltages, the current flow will start. If the common signals are present, V1 and V2 are same. So the potential difference is not available. Hence, no current is flowing here. The current flowing through RG is 0. So the common mode signal will not get amplified here. Only the different signal will get amplified. So in this way, we can reduce the common mode gain. Hence, the CMRR is increased. Also, the resistance are input resistance, high input impedance are obtained by means of this non-inverting buffers. So in this way, just by replacing the differential amplifier with the two stages of three op amps, so we can use this instrumentation amplifier in all the industrial applications. Hope you understood. Thank you.